Thanks, Henriette. Okay, so maybe we can start the recording.
All right, guys. So this is the last lecture on scattering amplitudes. And in this lecture, I'll talk about the double copy. So this will be a different presentation of the double copy than people normally do. I want to try to really explain to you what kind of miracle it almost is that this thing works. So we saw a little bit of a hint of the double copy already in lecture 2, namely when we bootstrap the free particle amplitudes from spinor helicity little group scaling. We found that the graviton amplitude was exactly the Yang-Mills color ordered amplitude squared. And so we talked about how this was a hint of seeing more generally at tree level that gravity is plus dilaton action is what you can get from somehow a double copy of Yang-Mills times Yang-Mills. So the goal of today's lecture is to really introduce you to this and how this crazy thing can even possibly work. There are double copy versions at loop level, specifically at the integrand level. Before you do the loop integration, there's a double copy proposal there. I won't cover that. I'll stick to tree level today. Okay, so to start with, let's talk about what the amplitudes in Yang-Mills theory actually look like. Well, the amplitudes in Yang-Mills theory, Yang-Mills theory has a non-abelian gauge group, and you can decompose the amplitude into single trace color structures at tree level. So here, again, we're at tree level, and I can write the full amplitude, the thing that has all the structure constants and all that in it, in a way where I organize all things that have to do with the color structure into a single trace of generators. And then the gluons that, of course, carry an index of the color group, an adjoint index that we normally suppress, that it gets organized into this part here, where I denote the fact that it's color ordered by the fact that it has square brackets there. And so you have to do permutations over the n-1 labels. Because of cyclicity of the trace, I don't do the permutations over all n labels. I basically keep line 1 fixed. And then I do perms over the n-2 other lines. So there's a total of n-1 factorial terms in the sum. This is just a nice way of keeping track of the amplitudes and not worrying about the color structure that sort of gets thrown away into a single trace, and we just have this cyclic color ordered amplitudes left. So these are called color ordered partial amplitudes. So for example, at 4 point, I could let alpha denote my color structure, and the n-1 factorial comes down to 3 factorial, so that's 6 different color orderings. I keep my line 1 fixed, and then I have these 6 other permutations of the 3 other lines. Okay, so that's the color structure. Now, when you're calculating color ordered amplitudes, the Feynman rules are very simple. They're the same Feynman rules that you normally use, but with a little extra restriction, namely that you have to keep the order of the external lines in the order that it's given. So you keep that fixed, and you never let lines cross. So you let no lines cross. So in particular, if I took the amplitude with color ordering 1, 2, 3, 4, I write my labels 1, 2, 3, 4 in a particular order that reflects the cyclicity also, because it's sort of writing them in a circle. And then I draw all the tree level diagrams without crossing any lines. So I have this diagram, an S channel diagram, I have a U channel diagram, and I can have a concept term. What I want to emphasize here is that this has something with an S12. This has something with an S14, that's what we often call U, and this term here is polynomial. It doesn't have poles. On the other hand, if I look at just flipping lines 3 and 4, the diagrams that I would have would be the ones that are compatible with the color structure 1, 2, 4, 3. And so as you can see, this gives an S channel exchange diagram, something with a pole in S. This gives something with a pole in T, because instead of U, we now have 1, 3 as opposed to 1, 4. And then it gives something that again is a polynomial term without any poles. So this you should contrast with what we get from graviton amplitudes. Graviton amplitudes have no color orderings, so all channels apply, and there'll be an S pole, there'll be a U pole, there'll be a T pole, and then some polynomial stuff in the Mandelstam in the spinor helicity variables. Okay. So when you look at this, what you should rightfully ask is, how can it possibly be that when I multiply together two of these color-ordered Yang-Mills amplitudes, how can I possibly get something with even the right pole structure as a double copy? In other words, if I multiply together, say, just this amplitude here with that amplitude there, the 1, 2, 3, 4 with the 1, 2, 4, 3, you see I'll double the S pole. That's bad because the graviton amplitude, no local amplitude can have a double pole. But I will generate the T and the U pole. On the other hand, if I just multiply this first amplitude, the 1, 2, 3, 4 amplitude with itself, I'll double the S pole and the U pole, and I don't have any T pole. So this sounds like rubbish, right? How can I possibly get a double copy to work as a product of Yang-Mills amplitudes? Okay, so let's talk about how this actually works. Well, so suppose that I have this A4, 1, 2, 3, 4, and I multiply it by the other one, 1, 2, 4, 3. So as I said, one problem here is that I double the S pole. So let's just solve that problem by multiplying by S. Actually, I'll put in a minus sign just for good measure. I'll multiply by S, and this suffices to get rid of the double pole in S. And we already generated automatically a T pole and a U pole, and then maybe some local stuff. So then the question is, does this actually work? Does this actually work to give the 4-particle graviton amplitude? Well, we know what these color-ordered amplitudes are when we pick MHV helicities. So these are the Park-Taylor formulas that I showed you last time. The S here becomes this product of an angle and square bracket. These are Park-Taylor amplitudes with the appropriate color orderings. Multiplying these things together gives you the expression here in black. And then I can multiply it and divide it by something that is really 1. And I can beat the heck out of it with momentum conservation. And what I'll end up with is this simple expression here, which is also the result of calculating the 4 Feynman diagrams and doing about 1 million pages of algebra to simplify it into this form, but that actually gives the graviton amplitude. By the way, each of these diagrams in the graviton amplitude, if you calculate them in a standard de Donde gauge, is about a page of LaTeX. So you have 4 pages of LaTeX that add up to this. So remarkably, this actually works. It gives the right answer. This naive way of just canceling the double S pole actually works. But there could be other ways of doing this, right? I also said, what if I just multiply the 1, 2, 3, 4 amplitude with itself? So let's try to do that. So now I take A 1, 2, 3, 4, and I multiply it by itself. Now the problem is that I'm going to double both the S and the U pole. So let's try our nice little approach again and say, we'll fix that. We'll just multiply by S times U. But these amplitudes don't have any T pole. So yeah, let me add it by hand. Okay, I add it by hand. I'll put in a minus sign. And remarkably, you can go through the calculation once again, and it works. This is really crazy, right? Because just getting the right poles is not enough to guarantee that you get the right amplitude. You also have to ensure that on those simple poles, that the amplitude would factorize correctly into 3-particle amplitudes. And it's absolutely remarkable that it does. That the product of Park-Taylor amplitudes can add up to something as simple as these simplifications of 4 pages of algebra. There was a student of my former advisor who actually verified this particular formula from Feynman rules in the mid-80s, and that must have been not so fun. It was just a 4.2, so that's a whole paper. Okay, so you might wonder now that we see that this actually works and computes the right amplitude. How can it possibly work with both of these formulas?
So, sorry, can I ask quickly? It works for these particular helicities, or does it also work?
Exactly. So I showed it just here as an example for particular helicities, but it actually works for all choices of helicities. It also works if you start mixing up the helicities so that you get the dilaton and axion contributions to the amplitudes. It still works.
Mm-hmm. I see.
So
Okay.
no matter which helicity assignment you do, this actually works, which is really remarkable. It factorizes correctly with all helicity choices, and it works works for all helicity choices. Great question.
Sorry, can I ask a question?
Yes.
So I'm a little bit confused on the helicity of the second amplitude of the first line in the next page. Why
Oh,
is
yes,
minus
sorry, I
minus?
messed it up. That should be pluses also there. Thank you.
Okay, thanks.
Great. Thanks.
Also, why couldn't you just add all the color orderings and then square it? Like, you know, in the beginning, you showed a formula like as a sum
Yes.
over all the permutations.
Right.
If you square it, then you should, like, what happens if you just square that?
So what if I just take this expression here and I just square it? Well, then I'll get something which has some weird squared set of traces or FABCs in it. But gravity doesn't have any ABCs, so somehow I needed to get rid of those. And it turns out, for mysterious reasons perhaps, that the right thing is to do the color stripped amplitudes.
Okay.
But it's certainly clear that I can't just keep it because I will need to get rid of it some way.
Right.
Great.
Yes.
Other questions?
The color stripped amplitudes, given that at the end we want to contract them with the TAs, won't they necessarily need to have some A in Cs so that we can contract with the trace? Or am I missing something?
Good. So when I write the color ordered amplitudes like this, they basically implicitly have these indices on them, but I don't keep writing them all the time. So they're always implicitly in the adjoint.
And so does the gravity, when we square those amplitudes, how do we deal with those indices? Do we also sum over those indices or we just ignore them?
No. So basically what those, so those indices just sort of tell you the color structure of this thing. So I mean, maybe it's wrong to say that they're really there, but really these amplitudes, like when I write the Park-Taylor formula, it's not like, so if I had the full amplitude, one way of color stripping would be keep track of these indices. In this formalism, there's nothing on the right-hand side in the kinematics. There are no FABCs. There's nothing that carries the adjoint indices in that respect. The color ordered amplitude really just is a shorthand notation that keeps track of the corresponding orders of the traces. So they, in a sense, they don't carry those indices so explicitly. I should perhaps have written this as just, so as I do here as the as just the permutations of the ordering of the lines, but they don't really carry the adjoint indices.
So if the square bracket amplitude doesn't carry the adjoint indices, then it seems like the one with round brackets will carry indices, and we don't want to happen. I'm just getting confused about how the
I understand. So maybe this was a bad way of writing it. Maybe the better way would have been to get rid of these indices up here, and then say simply that this is the, so this also looks weird, but this is maybe the better way of doing it. So I could put the indices over here, I guess. Maybe that would be a better way of thinking about it.
Okay, so the left-hand side is the one that does.
The left-hand side is, this is the one that carries the color structure. I should have written it this way, with the color indices sitting there and matching the color indices over there.
Okay.
And that would be normally how you do it.
Okay. Thank
Great. Okay, excellent. So good. So we have these two different formulas, and they both compute the gravity amplitude, but that may be a little weird because that would seem to require certain properties of the Yang-Mills amplitudes. In particular, if I subtract these two equations, then I can see that they have a common factor with the 1, 2, 3, 4 ordering, but the remaining factor would end up saying that the amplitude A1, 2, 4, 3 must be equal to S I can cancel out from both of them. And then it says U over T times A4, 1, 2, 3, 4. So there's a certain relation that this would imply for the Yang-Mills amplitudes. And that turns out to actually hold for Yang-Mills amplitude. This relation holds, and it's known as an example of a BCJ relation, and that stands for Bairn and Carrasco and Johansson. Similarly, you could have used any combination of the 6 other color orderings to do this with some appropriate Mandelstam factor in front. And the fact that these combinations with appropriate Mandelstam factors in front always give the correct double copy for the gravity amplitude implies a whole set of relation among these amplitudes. And those relations go under the name of KK BCJ relations. So let me actually explain what these relations are. So KK stands for Fleiss relations. And then there are BCJ relations. And at 4 point, what these look like is that the amplitudes with color ordering 1, 4, 3, 2, this has a trace reversal property, that this is the same as the 1, 2, 3, 4. So you see that goes in the opposite direction, 1, 2, 3, 4, 4, 3, 2, 1. So I'm just reversing the trace. And then there are 3 other relations of this kind. So there are 3 such relations. Then there's something called a U1 decoupling identity, which is part of the KK relations. That says that 1, 2, 3, 4. It basically says that if I consider particle 4 to be not just, so if I consider the gauge group to be UN and I pick the line 4 to be in the U1 part of that, it kind of has to decouple. So there's a U1 decoupling identity that says that line 4 in the U1 doesn't care where it sits. And so I can put it in all places and the sum has to be 0. And that's called the U1 decoupling. This comes about because the only color structure that you have in pure Yang-Mills theory is the FABCs. Okay, and then finally, there's an example of BCJ that we've seen that gives us that this amplitude is U over T times A4, 1, 2, 3, 4. So there's a total here of 5 relations among the 4 minus 1, n minus 4 factorial equals 6 amplitudes, and that leaves just 1. So there's only 1 independent 4-point amplitude among the 6 color orderings. In general, at n point, there are KK plus BCJ relations that amount to reducing the number of independent amplitudes from the n minus 1 factorial to n minus 3 factorial ones. And this is extremely convenient because the n particle version of the double copy involves precisely n minus 3 factorial amplitudes. So at n point, what is known as the KLT, Kawai, Llewellyn, and Tai formula for the double copy says that the graviton amplitude can be obtained as the sum over n minus 3 factorial color orderings of some left amplitude with color ordering alpha times some right amplitude with color ordering beta. Those are both summed over, and something that we call the KLT kernel, which is something you can think of as an n minus 3 factorial by n minus 3 factorial matrix with both indices of the color ordering. And this thing here is called the KLT kernel. And basically what that kernel is this set of Mandelstam variables that we saw before. So for example, at n equals 4, if I take this kernel to be 1, 2, 3, 4, 1, 2, 4, 3, that particular color ordering has a kernel which is minus s. And that gives that double copy that you saw before. So you might ask, but what if I pick different color orderings? What I pick different sets of n minus 3 factorial color orderings to sum over? Do I always get the same result? And the idea of the BCJ and KK relations is exactly that those guarantee that you get the correct same result, no matter which choice of n minus 3 factorial labels that you sum over in this formula. So this is some kind of convoluted product rule of doing amplitudes. And this kernel in particular is known. So when we look at this formula, we can think about it in the following way. It's something that takes a field theory on the left and multiply it using this KLT kernel with a field theory right. And from this, it produces a new field theory that we could call the left times right field theory. When you look at this, then there's a map for the states in the external states of the amplitudes, which is that if I have some state here with helicity left and some state here with helicity right, then that will map to a state with helicity left plus right. Why is that? Well, you can see this from little group scaling, that each of the left and the right amplitudes will scale homogeneously with ever a t to the minus HL on each side. And so necessarily, since the kernel only has Mandelstam barriers and doesn't scale on the little group, this will translate into t to the minus HL plus H right on the other hand. And this is how the double copy of two gluons with the same helicity gives you a graviton with that helicity. And likewise, that opposite helicity gives you axion and dilitons. Okay. Now, you might ask, so fine, Yang-Mills amplitudes satisfy these KK and BCJ relations that ensure that the double copy is independent of the basis choice. But are there other theories that do this? And it turns out that there are other theories that satisfy KK and BCJ relations. In the sense that this is what the tree amplitudes do. So they're also satisfied by the tree amplitudes of other models. In particular, well, it works for Yang-Mills. It also works for supersymmetrizations of Yang-Mills. And here, let me just give you an example. Our all-time favorite, n equals 4 super Yang-Mills. And then it works for a theory called chi-PT. What is chi-PT? It's a nonlinear sigma model. Nonlinear sigma models are something that we learned about in our lecture 1 when we did the soft bootstrap. And this is actually that color ordered adjoint model. In particular, it's a model that arises from the spontaneous breaking of un times un to a diagonal un. So actually, this is a model that describes low energy pions. Okay, so these are examples of theories I can use for input in my double copy. So let's say that this is the left sector or right sector, and then this is the left sector, just to maybe keep it logical. So left here, right there, I can put in Yang-Mills, I can put in n equals 4, super Yang-Mills, and I can put in chi-PT. So we know what I get when I do Yang-Mills with Yang-Mills. Then I get gravity, and let me just call gravity plus as an indication that the dilaton and action is also there. If I do n equals 4 super Yang-Mills with Yang-Mills, the supersymmetry is preserved in the sense that what I end up with is n equals 4 supergravity, SG for supergravity. If I do n equals 4 with n equals 4, the supersymmetries add up and I get n equals 8 supergravity. This map is symmetric, so I can fill in this entry. If I study the theory called chi-PT and I double copy it with the self, I get a theory that's familiar from lecture 1, namely the theory that we bootstrapped with sigma equals 3, that's called the special Galilean. This was the sigma equals 3. By the way, this is a sigma equals 1 theory. We'll talk about what sigma the other ones have in a second. Yang-Mills theory with chi-PT gives another familiar theory that I mentioned in lecture 2, namely Born-Enfeld theory, the theory that is the low energy effective theory on a space-filling brane, which in 4 dimensions has electromagnetic duality. That's a very interesting feature. So this gives Born-Enfeld. If I do the n=4 super Yang-Mills with chi-pt, I get another very relevant theory, namely the low energy effective action on a D3 brane, which is n=4 supersymmetric dBi, direct Born Infeld. Okay, so let's fill out these entries too, just for the completeness of the map. Okay. So there we have it. A set of basically something that looks like a multiplication table of a lot of theories that you have already learned about in these lectures and know from many, many other different contexts of physics. So that's pretty cool. The double copy interacts with all these different models. I mentioned before a couple of interesting properties, namely that you see here that chi-pt times chi-pt, two theories that have scalars in them with softness 1, double copy to something with a scalar of softness 3. This is actually a general pattern that the double copy enhances softness, and that's somehow due to the kernel, but it's a very non-trivial statement. So the double copy enhances softness in the sense that the soft limit sigma that we talked about in lecture 1, how fast this amplitude, well, how the amplitude behaves in the soft limit of a single particle, that in double copy is going to be whatever it is for the left plus what it is for the right plus 1. And this is consistent throughout this map. For example, in Yang-Mills, we saw that the amplitudes behave with a softness that is divergent. So they have a 1/p. So we should think that as it has a 1/p, but a 1/epsilon squared, right? So we should really think of that as sigma equals -2. And -2 plus -2 plus 1 is -3. And we saw exactly in the soft graviton theorems yesterday that gravitons have a 1/epsilon cubed in the leading order. There are many other examples of this in supergravity. There, for example, this is actually for the gluons and the the gravitons. H. In n=4 super Yang-Mills, there are scalars that are soft, but they're soft at order 1. So this is specifically for the scalars in n=4 super Yang-Mills theory. They go as order 1 in the soft limit. So if I double copy those with each other, I should add 1, and you see that you get scalars in n=8 supergravity that have 0 and vanishing soft theorems. Why do they scalars in n=8 supergravity? N is 8 supergravity has 70 scalars. These scalars are actually Goldstone modes. And they're Goldstone modes of something that you can think of as spontaneous breaking of E77, the exceptional group, non-compact exceptional group E77 to SU8. And this has 133 generators minus 63 generators that give exactly the 70 broken generators that account for the 70 scalars. And you can see that the double copy with an enhanced softness guarantee that these scalars have the vanishing soft theorems that should occur from this symmetric coset space. So that's an interesting story. Of course, it had to work this way because otherwise the amplitudes wouldn't match up. But it's just not the miracle of the double copying giving the correct pole and the correct factorization of the pole. It also gives the correct enhancement of softness that is needed for these maps to work. Was there a question coming up?
Yeah, sorry. Is there any pair of theories dual to just Einstein-Hilbert gravity?
Is there something that just double copies to Einstein-Hilbert, but not the axion dilaton? So at tree level, I can consistently truncate out the axion dilaton, but it becomes a little more of an issue when I try to apply something similar at loop level. It's not exactly the same formalism as here, but it becomes a little harder, and you have to work to project out dilatons and antisymmetric to index tensor in d-dimension or the axion in other cases, but people have been working on that.
Okay.
But it sort of can't work because the number of degrees of freedom that you double copy, they multiply, right? So two helicities in Yang-Mills times 2 helicity in Yang-Mills necessarily gives you 4 states. And so you need something else than just a 4D graviton.
Another question, is
Yes.
this the full map that we have, Or
Oh, this one here?
or do we know that these are all the theories, or
No, there
can
are
there
other
be more
theories
that
too.
we haven't found out yet?
There are other theories too. So I'll
Okay.
talk about that. So I have n equals 1 super Yang mills, n equals 2 super Yang mills, cases that I just left out here, but they also double copy the same way.
Mhm.
And then you could ask about higher derivative operators to these things. For example, chi-pt has a Wessel-Witten term. It turns out you can't double copy it. But there are other things that you
Okay.
can double copy. You can double copy f cubed in Yang-Mills theory, but you cannot double copy f to the 4 in Yang-Mills theory. So there's certain constraints. You can start doing these kind of analysis of what can and cannot be done. But the idea of that is something that I'll come to in a little bit. So ask again if you don't hear it directly. Okay, and another funny thing that enhances in the double copy is global symmetries. In the sense of global unbroken symmetries are also enhanced in a really kind of spectacular way. Global unbroken symmetries are also enhanced. And so let me give you an example of that. Well, actually, I'll give you 2 examples. So I mentioned in lecture 2 that Born-Enfeld has an electric magnetic duality symmetry. And that symmetry on the on-shell amplitude says that I have to have an equal number of positive and negative helicity photons in order to get a non-vanishing amplitude. So this is 0 unless n plus equals n minus. That's the effect of electromagnetic duality for the 3-level amplitudes. But Born-Enfeld, I've told you now, is supposed to be a double copy of Yang-Mills with this chi-pt theory. Chi-pt just has scalars, so it doesn't know anything about helicities. But Yang-Mills amplitudes has, of course, so this was Born-Enfeld, this is Yang-Mills. Yang-Mills amplitudes, as we know well now, has amplitudes that do not vanish when the number of positive and negative particles are the same. For example, the part-Taylor amplitudes with n greater than 4. And so these are clearly non-vanishing. So somehow it has to be that when I double copy these, then the sum over these different n-3 factorial color orderings must give 0 for any kind of helicity arrangements of this sort. And that miracle happens. If it didn't, then of course Born-Enfeld wouldn't be the double copy of these theories, but it actually does happen. And so it's another really quite interesting property of Born-Enfeld, or of the double copy. Another example is the story that n equals 8 supergravity arises as the double copy of 2 n equals 4 super Yang-Mills for 3 amplitudes.
Could I
N
ask a
equals 4
question?
super, go ahead.
Sorry to interrupt.
Right.
So this may be just a really silly question, but so we just talked about taking double copies where we just kind of do this special multiplication of the theories. So I guess my question is the natural question, can you do a triple copy? What about a quadruple copy? Is that a thing, or?
You know, that's an interesting question that I will say that's an open question if you can do multiple copies. But of course, with the idea of the group that the helicities will add up, you'll be sort of limited in the possible outcome of this, because you would quickly get into a situation with spin greater than 2, which we have learned is not allowed in flat space when it's coupled to lower spin. So I think it's sort of limited what kind of applications you'd have there for that. But you know, you might have something, but you would need something with a sort of interesting input structure to do it. But it's an interesting thing you can think about.
Thank you.
Okay. In fact, we will talk about generalizations of the double copy shortly, and that's where this is leading to. All right, so global symmetries. N equals 8 supergravity has an SU8 R symmetry that is unbroken. N equals 4 super Yang-Mills has SU4 R symmetry. So the double copy will manifestly automatically gives you SU4 cross SU4. But the fact that this actually enhances to SU8 in the double copy is again a little bit of a miracle of this thing, that it actually works. And it really does. So here's just another example of this kind of miraculous enhancement that the double copy does. And it has to do it in order to work, but it's still remarkable that something like this can work. Okay, so now there was a question about what else can you double copy. So I'm going to grab our table here and put it and shrink it so that I have room to write something else in this table. Are there any questions at this point?
Can I ask something?
Yes.
Is this a theorem that the symmetry must necessarily enhance, or can we possibly
it's
have?
Not a theorem, and it's something that would be hard to generally prove. But the statement that n equals 8 is the double copy of 2n equals 4 requires this miracle to happen. So if I didn't know that a double copy already existed, and somebody said, okay, you have to design something that takes products of amplitudes in these theories and generates something with the right poles, something that factorizes correctly on the right poles, something that has this miraculous enhancement of softness and enhancement of unbroken global symmetries. That seems like just asking too much, but the thing does it. And
all
so
known examples this works.
Are there other examples where this works?
No, I mean, in all known examples, this works.
So in all these examples here in the table, the required enhancements for it to work must happen, because otherwise it wouldn't have worked.
I see. Nope.
Okay, great. So so there's another theory that I'll denote by BAS, and BAS stands for bi-adjoint scalar theory. BAS. And that A should have maybe been big, so we can see that it's bi-adjoint. So BAS is bi-adjoint scalar theory. Now that also obeys the KK and BCJ relations, and I can put it into the double copy. Well, maybe I'll tell you first what it does in the double copy, and then I'll tell you what the theory is. So when I double copy it with Yang-Mills, I get Yang-Mills. When I double copy it with n equals 4 super Yang-Mills, I get n equals 4 super Yang-Mills. When I double copy it with Chi-PT, I get Chi-PT. And when I double copy it with itself, you guessed it, I get itself. So if you think about this as a map from field theory times field theory into field theories, this map we have now seen has an identity element. So basically the bi-adjoint scalar model is the identity element of this double copy. The identity of what we can call the KLT algebra. And what is that algebra? It says that when I call the bi-adjoint scalar theory the identity element, I have an identity that says that this thing double copies to itself. If I double copy a left theory with it, I get the left theory back. And if I double copy the right theory with it, I get the right theory back. So this is what I would call the KLT algebra. Now, your first question may be, okay, so now it has an identity. Does it also have an inverse? Is this really a group structure? But it's not a group. There's no, as we know it at least, there's no inverse to this map. So it's just an algebra, not any kind of group.
Sorry, does the kernel depend on the theories, or is the kernel independent of the theories?
Exactly. When you change, and this is where we're getting to, if I were to change the multiplication rule, it is logical that I also have to change who is the identity element. And so if I want to change my multiplication rule, I will also have to change the identity element. And that actually is a way that I can help finding out generalizations of the double copy. And this is where we're going. Great question.
excuse me. Is the inverse the only thing that's lacking? Does this have a monoidal structure?
Sorry, I couldn't hear you.
Is the group, or excuse me, is the inverse the only thing lacking? Does this have a monoidal structure, or is it just stops at the algebra?
So it just stops as it being a multiplication rule that is at this level that I presented it here is abelian. The ordering doesn't matter. It has an identity, but it's lacking. It's just lacking the inverse.
Thank you.
Okay. So what is this bi-adjoint scalar model? Well, it's a model with a bi-adjoint scalar, as you might have anticipated. That means that it's a scalar that has an index in the adjoint of one group and an index in the adjoint of another group. And so I'll call these groups G right and G left. And you could, for example, think of this as being a UNR times a UN left. Now, from what I've written here, you probably think that I'm left-right confused, and that I wouldn't blame you, but it's actually it turns out to be the right ordering, that right is on the left and left is on the right. I'll show you in a second. So this index belongs to left, this index belongs to right. So this is somehow a similar structure that you might have seen in the large N lecture by Mukund, that there was sort of scalar fields with multiple adjoint indices. Here we don't care so much about large N because we're only at tree level. So everything is just deleting large N, so to speak. Anyway, what this action then is, the bi-adjoint scalar has a Lagrangian, which has a kinetic term, which is what you would suspect it to be. So it has implicit index contractions over this. And then it just has one interaction term, namely a cubic interaction term with a coupling that I'll call G. And then it has a contraction with the structure constants of our left and right groups and three fields. So it has this cubic interaction. Now, if you were to try something like this for a scalar with a single adjoint index, it wouldn't work because a single adjoint scalar contract with an FABC would vanish because of the antisymmetry of the ABCs and the symmetry of the three scalars. But when I doubly contract them in like this, it is non-vanishing. Okay, so the amplitudes of this theory have a color ordering, and they're color ordered with respect to both the right and the left. So I have a color ordering, and I'll denote the three amplitudes in this theory by MNs. And so they carry a double color ordering. And this is with respect to the right, and this is with respect to the left. So what it means is that when you write down Feynman diagrams for these amplitudes, they're only cubic vertices. It's very simple. There's a standard kinetic term, and you just have to write down diagrams that are compatible with both the color orderings. So in particular, 1, 2, 3, 1, 2, 3, a three-particle amplitude is just what you get out from the scalar. That's a G. If I were to change the ordering here, 1, 3, 2, I'd get minus G. That comes from the antisymmetry of the Fs, and I'm only changing the ordering in one label. If I calculate the 1, 2, 3, 4, 1, 2, 3, 4 entry, it has two diagrams, 1, 2, 3, 4, plus a U channel, 1, 2, 3, 4. So this becomes G squared over S plus G squared over U. Let me just do one more so you can see the idea. I'll now interchange the labels in the second color ordering. So it's 1, 2, 4, 3. And now I can see that my compatible diagram for this is 1, 2, 3, 4. It has both of them have a 1, 2 and a 3, 4 adjacent. So this is a diagram that gives G squared over S, but it has a minus sign because of this interchange of order that I had before. And then that's all there is. This guy can't have a U channel because a U channel violates the color ordering of the second order, and a T channel would violate the coloring of the first one. So you just have to have the compatible ones. Okay. So what does it mean that this theory double copies to itself? So what does BAS times BAS equals BAS mean? In other words, what does 1 times 1 equals 1 mean for these amplitudes? So written out explicitly, it means that if I take some amplitude with some color ordering, with some color, and this is delta and delta and gamma, then I do my usual sum over n minus 3 factorial color orderings of alpha and beta each. And then I put in my left copy with my kernel, and then my right copy. And then the indices that sit here and here are simply just inherited. So now you see a little bit why I called things right times left before, because this is a left index. This is a right index. And so on the other hand, this is something index that has to match over here. So this has to match that this is a left and this is a right. And therefore this has to be a right and this has to be a left. Okay? So that's why there was that flip in left and right for the biadjoint scalar model to match up with the double copy. Now this looks exactly like matrix multiplication. So in fact, if we let Mn with an underline denote an n minus 3 factorial times n minus 3 factorial submatrix, and I let Sn similarly denote an n minus 3 times n minus 3 matrix, submatrix of matrix, then that whole equation says that Mn is equal to Mn multiplied as a matrix with the kernel times Mn. And so what I can do now is multiply this from the left and the right by the inverse of M. So multiply from left and right both with Mn inverse. And then what you'll see is that you get that Sn is necessarily the inverse of that matrix. So someone asked before, what is the link between the biadjoint scalar, the identity element, and the multiplication rule? This is exactly the link, that the multiplication rule defined by the KLT kernel must be the inverse of this submatrix of amplitudes of the biadjoint. So that's very cool. So this cleanly links the identity element and the multiplication rule in the story. Okay. By the way, nobody complained and asked, are these matrices even invertible? It turns out that yes, they are. But that's of course a necessary condition for this to work. So let's just see how this works. See, well, give me some good color here. Let's make it blue. So at 4 point, what would I get? So S4, 1, 2, 3, 4, 1, 2, 4, 3, n minus 3 factorial at n equals 4 is just 1, as we know. So this should be the inverse of Mn 1, 2, 4, 3, 1, 2, 3, 4. And we know what this amplitude is. That was, oops, that was something we calculated before. That was the thing that just had the S channel. And so this gives minus S divided by G squared. And that was why, going all the way back to the beginning, when I showed you how this double copy worked, this was how it worked. Up to that factor of G that I didn't include, this was exactly that factor that came out from the kernel at 4 point when I multiplied the two different color orderings together. And you can do the same thing for relating the S1, 2, 3, 4 at 1, 2, 3, 4 together, and you'll see how that automatically works. Okay, so now we have identified the role of what 1 times 1 equals 1 means in the double copy. And let me just pause for a second for questions. Okay, well, So we know some meaning now of 1 times 1 equals 1. It's that it links the inverse, the identity element with the KLT matrix as an inverse. So what is the role of R equals 1 times R? What does that mean? So we could now write down an example of this. A right with some color ordering is equal to this usual sum. And then we take our identity element and put in our usual kernel and multiply in our right amplitude. Okay, so that is what this means. And now, when I write this out as a matrix in the same way as before, I would have Mn times Sn dotted in with a vector Rn. So these are not matrices. This is an n-3 factorial component vector. And you can think of the right and left copies as being rows and columns respectively. All right, columns, I mean. Oops. So that's a column vector. Okay, all right. So if I then use that S was really the inverse of Mn, then it almost seems as if these identities are completely trivial. But the thing is that I have a choice of basis, and I can pick different choices of n-3 elements. That is what gives a non-trivial relation here. And so these are actually true constraints on the amplitudes, and you could work out to see that these non-trivial relations that they give are completely equivalent to the KK and BCJ relations. And for example, you could see this by taking A4, 1, 2, 4, 3 with M4, 1, 2, 4, 3 that has to match, and then do 1, 2, 3, 4 times 1 over, and here comes the kernel part, M4, 1, 2, 3, 4 with 1, 2, 3, 4, and multiply this by A right, 1, 2, 3, 4. That's how the indices match up. Then this part here we've seen is minus G squared over S. This part here is 1 is G squared over, is G squared times 1 over S plus 1 over U. And we'll have to take the inverse of that, and you multiply these things together. And what this results in is the BCJ relation that I showed you originally, namely that this becomes UT times A4, 1, 2, 3, 4. And that was exactly the BCJ relation that I showed you very early in this lecture. Okay, so the upshot is that the two algebraic relations, right equals 1 times right, and left equals left times 1, they give you two things. They ensure the basis independent of which n-3 factorial choices I make for my KLT sum. And they do so by imposing on the amplitudes the combined KK and BCJ relations. So this algebra actually has a meaning. I want to come back to one thing about 1 times 1 equals 1. Because there's an illustrative thing to look at with this. So once I know that the KLT matrix is the same as the inverse of the Mn matrix, I can write this statement as Mn equals Mn, Mn inverse times mn. And again, this looks really trivial. And it is trivial if I pick the same n minus 3 factorial basis elements for each one of them. Then this would trivially hold because they're just inverses of each other. But I don't have to pick the same basis. And so with different basis choices, this is non-trivial. It's non-trivial in the following sense, and I'll show you this by an example. So let me write out this equation here at that 4 point. And I know it's a lot of writing 1, 2, 3 in different orders, but I want to illustrate this point. So I have my basis choice. And so far, everything that I've written down looks the same, but now I'm going to flip these two indices here. And so this is my left amplitude. Here comes my right amplitude. 1, 2, 4, 3, 1, 2, 3, 4, divided by M4, 1, 2, 3, 1, 2, sorry, 1, 2, 4, 3, 1, 2, 4, 3. Okay, so we have flips. That means that we have different bases in different places. This is from the kernel.
So just to
Now,
make sure, when you say different choice of bases, this is in doing the sum, the matrix multiplication.
So this is doing exactly this matrix multiplication up here. So when I pick these are each n minus 3 factorial, but I have n minus 1 factorial orderings to choose between. So I could pick, if I picked all of them to be the same n minus 3 factorial, these would be just inverses of each other. But if what I'm doing here is that I have just 1 for the 4 point, and I pick my one basis choice to be 1, 2, 3, 4. And here I pick another basis choice, 1, 2, 4, 3. And that gives me something non-trivial. And if I then multiply the denominator here over to the other side, then you'll see that this is exactly the condition of a vanishing determinant. So this is equivalent to saying that the determinant of the following matrix vanishes. I'm going to see if I can save a little time by stealing elements from here. Oops, I didn't mean cut. Oh, it stole something from me here. All right, sorry, maybe this was not saving time, but the intent was good. I'll write the last one. So the statement that this 1 times 1 equals 1 holds is exactly the same as saying that this 2 by 2 matrix holds. And if I had chosen any other basis up here than what I did, the 1 times 1 statement equals 1 is equivalent to saying that the n minus 1 times n minus 1 matrix of all possible orderings of inequivalent orderings has rank n minus 3 factorial. So the statement is actually that not only are the n minus 3 factorial matrices invertible, but the actual max rank of that whole matrix of possible color orderings has that same rank as our n minus 3 factorial ones. And so that is another relevant statement. So the n minus 3 of all color orders. Okay, so that's the idea. All right, so we have seen that the biadjoint scalar theory generates elements that have this property, that the matrix of n minus 1 factorial times n minus 1 factorial of all colorings has rank n minus 3 factorial. But you might ask if there are other choices of the mn amplitudes that have this ordering. So are there other choices of mn alpha betas such that the rank is n minus 3 factorial of the full n minus 1 factorial by n minus 1 factorial matrix of MNA alpha betas. So think about it again. I have this biadjoint theory with its Kuiper interaction. I can compute the amplitudes. I have n minus 1 factorial different orderings, and I can put them into some n minus 1 factorial by n minus 1 factorial matrix. If I start changing the theory that calculate these, what is going to be the rank of that matrix? Are there other choices so that it has the right rank for the double copy? And it turns out that the answer is yes, otherwise we probably wouldn't be talking so much about it. And here is a particular choice that works. So here's 1, 2, 3, 4. I'll just write a couple of the elements. If I take this to be tangents of alpha prime, and you might be suggested that there's an alpha prime here. So hold your breaths, but not too long. Remember to breathe. Here, this was supposed to be a U. So there are tangents that sort of replaces what we had before as propagators. If I do the other one, 1, 2, 4, 3, I'm supposed to use here minus 1 over sine of alpha prime pi t s. So basically, this replaces what we did before in the biadjoint scalar with something that looks a bit crazy. It replaces these propagators by tangents and sines. But nonetheless, and this is due to work by Misera around 2016 or so, what you can show is that when you use these amplitudes, then again, you get rank n minus 3 factorial. And when you then compute a KLT kernel from the inverse of these n by n minus 3 factorial by n minus 3 factorial matrices, then what you get is precisely what is known as the string theory KLT kernel. And what does that do? It says in matrix form that if I use this kernel to calculate amplitudes, but I use it together on the left, on the left and on the right to calculate. Oops, see here. Left and right. Then that's our strings kernel. And these amplitudes right here are open string amplitudes. And the result on the left-hand side is the closed string amplitude. And this was, in fact, how the double copy was originally discovered. So we've gone completely backwards. We try to construct things from a bottom-up approach, what can even have the right poles. And then we solve the same equations and see that there is a solution, and that solution is, in fact, the string theory double copy. And this was all the way back to it's 98 or 90, 95 or so, 95 or 96. Sorry, 1985 or 86 or so. And this was how it first was discovered by Kawai, Levellum, and Tai. And the alpha prime going to zero limit of this, the leading order thing you get, gets us the field theory KLT that we were just talking about all along. Okay, so this is pretty cool. So there's a solution here. And this is the string KLT kernel that satisfies the 1 equals 1 times 1, but now it's KLT with alpha prime, and it's open string, and it's these funny kind of amplitude looking objects that go there. But then you might say, what is the then equivalent of the two other identity element relations, left equals left times 1 and right equals 1 times right, when these are the alpha prime corrected versions and the open strings? And these are a set of relations that are obeyed by the open strings that are open string tree amplitudes that are known as monodromy relations. And so open string tree amplitude monodromy relation. I should emphasize here, these are all at tree level. So in string theory, if you have learned about string theory scattering amplitudes, you know that you calculate them using vertex operators. And you may have seen that closed string vertex operators are product of open string vertex operators. So you might see, oh, that's why there's a double copy. But when you calculate the string amplitudes, you have to integrate over all the insertions of these operators. And it's highly non-trivial that there's a factorization that happens after you've done that integration. But that was what K, L, and T showed. Okay, so now the question arises if there are other solutions to the double copy equations. Other solutions for Sn equivalently for who is the identity element. And there, one thing to think about is that these amplitudes that the string has, they don't look like amplitudes. They have crazy set of poles. They have infinitely many poles because they're tangents and sines. But if I expand an alpha prime, basically what they give me is a set of higher derivative corrections to the biadjoint scalar model. So the thing you could go out and look for is some new model, which is biadjoint scalar model plus higher derivative corrections. But of course, then it's not clear that if I just start adding higher derivative corrections and all sorts of ways that I can come up with, that I would get something that satisfies the correct rank condition. In particular, I would want the rank to stay n-3 factorial, because otherwise, when I take a low energy limit and get rid of the higher derivative corrections, I would want something that reduces to what I had before. And remember, I had inverses of n-3 factorial order matrices. So if I suddenly have bigger matrices, then it would be, the construction would become singular. And that would be very weird. It would be a weird mixing of UV and IR physics. So I want to maintain rank n-3 factorial. And then relations such as these determinant identities would have to hold. And so you can see, for example, even here at 4 point, that if I start modifying what these different entries are, these different amplitudes by adding higher derivative corrections to the biadjoint matrix, this determinant may no longer vanish. And this is indeed true. And one of the things you can show is that the simplest higher derivative correction you could add is something that doesn't even look like a higher derivative correction, basically something like a phi to the 4 interaction. Then you can add d squared phi to the 4, d to the 4, phi to the 4, plus, 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 plus. And you know from lecture 1 that we can bootstrap these by just using Mandelstam polynomials. And then when you then put this in to the condition that 1 times 1 equals 1 with the rank n-3 factorial, you'll find that this guy is never allowed, but certain combinations of these ones are. There's a single combination of this one that is, but they have very particular coefficients. And these coefficients that you get, they will generalize the alpha prime expansion of the strings kernel.
Henrietta, you have about 5 minutes.
Great, that's perfect. Okay, so the idea of what you can do with this is that you can try to look for generalizations of the double copy. And this will be something that you can read about in a paper that hopefully will come out soonish by Wanheng Chi, Callum Jones, Sruti Paranchapi, and Aiden Herdeske, that you might have met because he's right here, and myself, in hopefully somehow the coming weeks or so. So these ideas of generalizations and this way of presenting it. But I want to finish in the last minutes by trying to give some perspective both on the double copy and on the amplitudes program as a whole. So in these theories that we have been double copying, there are lots of different theories that have been input. I've talked about Yang-Mills. I talked about Chi-PT. by adjoint scalar gravity, n equals 4 supersymmetric dBi, and special Galilean. And these are really widely different theories when you think about them. So Yang-Mills theory is a nice renormalizable theory, relevant for nature, gluons at the LHC, and so on. KPT is also relevant in nature. It's a nice EFT for pions. Bi-adjoint scalar model is not a nice theory at all. It's like when you first learn about field theory and you learn about phi cubed theory, and then you say, great, it's fine for learning how to do Feynman diagrams, but the potential is unbounded from below, and it's really a sort of a sick theory. So this is potential unbounded from below. It's weird how such a sick theory should play such an important role for things like the double copy, but it seems to do. It does that. Gravity is, of course, non-renormalizable, but it's, of course, a great EFT. Very useful in nature. Then n equals 4, super dBi, low energy action on D3 brains, great theory. It is UV complete. And then special Galilean is in the swampland. By itself, without any other leading terms, it's a sick theory that doesn't have a UV completion. It really lies in the swampland solidly. But then the double copy connects all these theories. And that's just sort of crazy. What does it all mean? This is a very different way of slicing the landscape of field theories, whereas conformal bootstrap focuses on conformal field theories. I should put in here another case, which is n equals 4 super Yang-Mills, right? That is a CFT. How can it combine all this different stuff? So I think that is an interesting aspect of the double copy that we still need to try to understand a little bit better. So in these lectures, I've talked about a soft bootstrap for EFTs using soft theorems and Atlas zeros. I've given you a toolbox of 40 helicity, spinor helicity formalism. We talked about the divergent soft theorems and some really nice fundamental properties that you can derive from them. And then we talked here about the double copy. For the double copy, there are many other ways of doing double copy. Here I focused on the KLT form and working on generalizing it. In particular, the generalizations that we have is sort of kind of a heterotic version as the setup type 2 version. There's something called the CHY scattering equations that gives a very nice formalism for taking soft limits, but also gives a different perspective on the double copy. And then there are BCJ, color kinematic duality, which is a very useful way too, and the method that tends to generalize to loop integrands if you want to do double copy there. Then the idea that there's a double copy for tree level, well, tree level is supposed to capture the classical physics. So does that mean that equations of motion, solutions to equations of motion also have some double copy? So people have explored if solutions in Yang-Mills to the equations of motion can double copy into solutions of gravity, at least in a perturbative sense. And that is a classical E&M double copy version. And then there are interesting questions too about the geometric origin of the double copy that people have explored in a variety of papers. So there are a lot of different perspectives on the double copy and a lot of different implications of the double copy. There are also many different other studies of amplitudes. And so I presented to you just a very small selection of things that people are interested in working on. Oh no. Here we go. Is this back up and sharing? No? Okay, are we back in?
No.
We'll be there a second. Here, we're almost there. Here we go. All right. So there are amplitudes and a whole different set of subjects. There are positive geometry that you can ask Aiden more about. There is amplitudes and phenomenology, so amplitudes and pheno. There's amplitudes for gravitational waves. Applications there. There are amplitudes and cosmology and geometry put together. And then finally, there's amplitudes and your contributions. And so I hope I have inspired you guys to read more about amplitudes and listen to more talks about amplitudes and not completely scared you away from it, because there are a lot of fun things that are going on and there are a lot of different ways of applying these methods. A student of mine worked on black holes and studies of swampland from black holes perspectives and used amplitudes methods for a certain non-renormalization theorem in that context. So things that you might not have thought of using amplitudes for, the techniques, the way of bootstrapping high derivative terms, all these different things can be put together, and it's nice as a toolbox to have to address different kind of problems. So please come together, please come and talk. I look forward to seeing you guys in discussions tomorrow, and of course also answer questions now. So thanks for being here.
Thanks a lot, Henriette. Do we have any quick questions?
I have a question. So every single amplitudes thing you did, except the string theory one, was in 4D, but string theory was a 2D velocity theory. What is the amplitudes program like in 2D? Are there more examples of double copy, or is it 4D that's special?
So everything I did when I talked about the KLT formulas and the kernels in general is general dimensional. So I would say 3 and up. 3 can have a little bit more constraints, but at least 4 and up is completely general. This is all just Mandelstam variables. When I gave you specific examples of using Park-Taylor and formula and so on, for convenience, I did it in 4D, but these also hold in any dimensions. So these double copy relations that we wrote down, that whole table, is d-dimensional, but the degrees of freedom count, of course, changes in different dimensions. When you think about generalizing the kernel, we have thought about 4D and up. When you're doing 3D, there are a little bit more kinematic constraints on the amplitudes. But then you ask about 1 dimensions. And in 1 dimensions, in terms of scattering, there's not a lot that can happen. I mean, I can have particles come in and go back out, or they can come in and go past each other. So in certain sense, 2D scattering is kind of trivial, which is also why in 2D you can circumvent things like Coleman-Mandula theorems and so on. So did you have something more specific in mind for 2D?
Mostly, does Chern-Simons feature anywhere in any of this? Because that's like one of the best understood
Very good.
theories.
So I would say, so if we're thinking about 3D and Chern-Simons theory, so my former collaborator, Yuten Huan, did a little bit of work on that. So one interesting aspect there is, of course, ABJM theory. And that has a color structure, of course, and you can start trying to double copy this into some kind of 3D version of supergravity. So there is a story there, which I would have to look up what the situation is. Someone asked about whether you could have a triple copy instead of double copy. If you wanted to explore that, the 3 algebra of things like ABJM might be a context in which you could play around with it. I don't think anybody has really tried that.
Thank you.
These double copy relations that you mentioned, you only mentioned for like SUN Young-Mills, and then the Biot-Chern scalar has UN. Does it also work for any other group, or? So
the group structure is not so important because we just basically factor it out. So what exactly which gauge group we have or which color group we use is not playing a big role so long as it's non-abelian. One thing we do see happen is that in the standard double copy with the field theory one that I started describing, they're just antisymmetric structure constants in everything in Yang-Mills theory and N=4 superangles. Everything is just FABCs. But of course, you also have other color tensors that you could write. You could think about having a DABC. You could have the fully symmetric 4-index DABCDs. You could have all sorts of different color structures and invariant tensors. And what we see is that the moment we start generalizing the kernel, in fact, string theory also has it, these kind of different color structures begin to enter. So when I said that there are terms of this form here, d squared phi to the 4, they necessarily involve some terms that have DABCs in them. So the fully symmetric, the type of structures that show up in anomalies, if you if you're familiar with that context. So these contexts shows up there. And because they're DABCs, they modify the U1 decoupling identities. And that's also a well-known feature from string theory, that the string monodromy relations will modify the U1 decoupling relations. And we see that from a generic point of view. What is different in our case is that the left and the right sector are treated differently. That is a new feature, that in the strings kernel, as well as in the standard field theory kernel, left and right enter symmetrically, but it no longer does in our generalization. So I can, for example, turn off U1 decoupling on the left, but not on the right, if I wanted it.
Yeah, thanks.
The alpha prime kernel that you wrote down depends just on S. Is that structure understood?
So very good. So it's an interesting feature when I look at, and this is the thing you're referring to, this depends just on S, whereas the other ordering here, that also has a U dependence. But you can see that when I expand this thing, it has two special features. When I now lead, well, okay, we can put in the factors. So I have some leading order, which, so good. So when I expand the kernel here, let me write that. S4 alpha prime will be the inverse of this thing then, with 1, 2, 4, 3, 1, 2, 3, 4, will then be minus sign alpha prime by S. And when I expand that in small alpha prime, I get the leading order S, I get 1, 6 alpha prime pi S cubed, etc. So you see two special features here. The one you mentioned, that this thing only depends on S. That seems very special, because if I was generically just characterizing higher derivative operators here, I would also write things that depend on T, or in principle U, but of course those are related. So I will write general polynomials in S and T, but we see that that's not allowed. The other thing in the strings case, but the other thing that is special here is that there are only odd powers. So the odd powers means, and in this particular case, it means that the equivalent of S to phi to the 4 is absent. It's a little unclear how that comes out. It's a power counting, but that is basically what this means. The phi to the 4 is not allowed. And we know that this is true because it doesn't satisfy the correct rank relations. But why string theory has this successful form, as opposed to writing down a general polynomial in S and T, is one of the interesting questions that we would like to understand better. So now we have a general solution for this power expansion. It depends in general both on S and T, but with specific combinations thereof. And why it is the way it is in string theory is perhaps a little bit unclear. But one thing that is important is that the kernel, as it comes out with the signed feature here, of course, has an infinite set of specific zeros. And that turns out to be very important, because when you double copy the string, the open string amplitudes, of course, also have infinitely many poles. So these come from all the basically massive modes of the string. And all these infinite different modes that you will have, they would also double and give you double poles in the closed string. And you can't have that. So the zeros of the kernel are extremely important for canceling those double poles, in analog to how I presented this in the first place. So in some sense, we know why this kernel has to have the zeros the ways it has, because it needs to cancel things that would otherwise give double poles in the double copy. So there's a clean connection between what this kernel can be and what the amplitudes that a double copy, what they are. But if I did it from a bottom-up approach, where I don't know anything about the massive states, I'm just looking at effective field theories, one thing we would really like to understand is exactly how these constraints on the amplitude comes out. So that is an open question. And combining this thing with swampland conjectures and so on is definitely one of the things we would like to look at.
Very good, thank you.
Okay, let's finish the discussion there, at least with the recording. And